Hello, and welcome to the CHA E-beam Evaporator Training and Information Guide. This presentation is meant to give you an introductory overview of operating the evaporator so that you might minimize the amount of necessary in-person training time. Electron beam evaporation involves focusing an intense electron emission at an element or inorganic compound to heat it to temperature sufficient to evaporate at a desired rate. During this, a hot filament emits electrons, which are steered by both permanent magnets and coils so that they exclusively strike the desired evaporant. These are some typical views of an electron beam evaporator and its components. This is a full assembly. This round component is what's called the hearth, and the holes in it are called pockets, which sit crucibles full of the desired materials. Under the front of the assembly, there sits something that looks like this. This is the emitter, which is responsible for generating the electron emission that gets focused into the beam. This is a cross-section representation of a typical evaporator. The hearth is covered by a plate so that only one pocket is exposed at a time, and the hearth rotates to move the desired material into position. There are models which expose two pockets at once and have two emitters so that co-evaporation from one source is possible. All evaporators in the K&I, however, are single emitter. In front of the gun there is an assembly of coils, which focus the beam from the emitter up through a hole and down into the pocket. The material is heated by the beam, causing vapor to coat everything in line of sight. This is a top view of a crucible. The beam will move around in the pocket in some defined path, often called a sweep. The purpose of the sweep is to assist in heating the material uniformly. The MK40 by CHA has a 6-pocket E-beam evaporator. 2 of the pockets are reserved for gold and platinum, but the other 4 may be loaded with a wide variety of metals and oxides, such as alumina and silica. The chamber utilizes a lift-off dome, which holds wafers in a spherical radius relative to the evaporation source. This optimizes uniformity across the wafers and is ideal for lift-off processes. There are a few dome types, but the main one holds up to 22 4-inch wafers. Pockets in this evaporator are pretty large, allowing pretty thick layers up to about 5 microns per crucible when properly filled. One can feasibly evaporate many materials at rates exceeding 100 angstroms per second, though most users will default to 1 angstrom per second rates. Users wishing to deposit at high rates must contact K&I staff. Base pressure is approximately 5 e to the minus 8. But due to the fact that the majority of the chamber is vented to load, most users will wait until a pressure in the low e to the minus 6 range to begin deposition. This takes 20 to 30 minutes of pump down time. Directly below the computer monitor, you will see the IC5 deposition controller. This controls beam power, measures deposition rate from the crystal thickness sensor, stores loaded layer processes, and all the necessary data for accurately measuring thicknesses of various materials. Below this, you will see the sweep controller. This will tell you what sweep pattern is currently running, allow you to change sweep patterns, and gives a basic visual representation of the pattern. Below that, there's the main power controller. This shows the high voltage status as well as the current beam emission. The power is controlled automatically by the IC5. Additionally, you will see a temperature gauge for the cryopump, which should read 12 or 13 Kelvin. Do not use the system at all if you see it above 13 Kelvin and notify staff. There's a temperature gauge which estimates the temperature of your substrates, a dial for setting the dome rotation speed, which should be set to 20, and a readout for the pressure gauges. This is also found on the software. The EMO button is for true emergencies only. It will totally cut power to the entire system. This is for serious hazards, such as electrocution risk, serious earthquakes, fires, and floods. There is a software abort option for more typical aborts. Looking to the monitor, we see the main software interface. Notice the 5 main buttons along the top. This screen, the pumping control panel, is usually up. If not, go to Navigator panel and then select pumping control to open it. From here we can control valves, open and close the shutter, vent and pump the chamber, manually rotate the dome, and select pocket positions. First, notice the top left button. It says manual, and above that it says state, and next to that it says none. You will also notice these valve buttons. They are all grayed out, as well as the rotation of the shutter and the buttons which allow you to open and close the shutter. They're all grayed out. These are the ways you know that you are in automatic mode. If you hit the manual button, all of these grayed out buttons will become bold, and you will be able to use them. Also, where it states at the top left, where it says none, will begin to say manual. This will be important, as we will need to go into manual mode to do certain things. Note that this is a touchscreen, and you can accidentally open and close the wrong valve and do potentially very bad things if you are not careful while operating in manual mode. Let's take a closer look at this screen, as it is a drawing of the chamber and tells us about what's going on in that moment. The main chamber area animates to show you things like dome rotation. This will rotate. Whether the filament is on or off, this orange box region will light up. The shutter open or close, this little teal line hanging over the middle means the shutter is closed. It'll get shorter, indicating that it's swung out of the way. If the motor is rotating the hearth, this will light up with a yellow background behind it. Whether or not the high vacuum valve is open or closed, this is a literal drawing of what the valve is like. Right now, this big flange is back away from the chamber, and therefore it's open. It will move over and press against the side, indicating that it is sealed. You'll also see the high pressure switch light turn green, meaning that this valve is closed, and there is a large pressure in this piston forcing it closed. At the bottom, you'll see the current pocket selection and the position that it's currently in. If you select, let's say, 3 and this is in 6, it means you'll then see it go to 1, then 2, then 3. At the same time, you'll see this light up, meaning that it's moving. So all these things connect together and directly talk about what you are doing in that moment. You can also see, like I said, if it's actually rotating. Actual right now is 0. In this case, it wasn't turning. The set point would be 20. So if we hit start rotation in manual mode, it would begin to turn and it would go to a speed of 20. Now you'll see I've entered manual mode, as it says manual on the top left. And the buttons on the bottom have all become bold. I can now use them, as well as these valve buttons have become bold. So if I click them, they will open and close. Let's click on where it says Pocket Selection. When we do that, this window pops up, allowing us to type in what pocket we'd like to choose and hitting Enter. And when we do that, it will move to the desired pocket. The hearth will rotate there. We can also then close and open the shutter to be able to look in and check out the materials. This is something we'll need to do when we load and unload samples, as we will want to check the status of our materials before we begin evaporating and after we've evaporated to see if anything strange has happened. Now let's start to set up our run. Notice I am back on automatic mode, as these are grayed out. You want to be in automatic mode anytime you are running either chamber vent or pump down. Chamber vent is currently selected and pump down is in gray. You can also see that the T-shaped region right here of the vacuum tube is blue, and that the ion gauge is off and that the pressure is too high for an ion gauge to run. That's because we are currently venting. This is blue, indicating that nitrogen is flowing into the chamber. In addition to that, you can see that the high vacuum valve is extended, showing that it has valved off the cryopump region. This region remains under high vacuum while you vent the main chamber. This will stop automatically on its own. The blue T section will go gray. Another way to know if a process is still running is by looking at the top left where it says state. Here it's shown as running. Otherwise it will simply say none or OK. Once this auto vent is complete, you will need to manually vent a little more to actually get the door to the chamber open. To do this, we will click manual to go into manual mode, and then click on the vent valve to open it manually. Be very careful not to accidentally click the rough valve, or you will just start roughing the chamber. Once the chamber door pops open a little, you can close the vent valve. Now we've opened the door. On the left is what you will immediately see. At the top is the dome, where the substrates will be placed. If we zoom in on that, we'll see this is what the slots look like that hold a 4-inch wafer. They sit right along in that little groove, and there are 2 clips on either side to hold them in place. If you have small chips, you can affix them to a carrier wafer with copper or Kapton tape, and then place the carrier wafer in one of these slots. Looking down into the chamber, we will see the shutter. On the main control screen, we can hit the shutter open button to reveal the hearth underneath. The hearth is able to rotate, while this beveled cover over it remains fixed. Notice the curved U or V shape that both the hearth and the cover have. These should align with each other as shown, and in the pocket, there should be a very centered lump of material, and the pocket itself should be very centered relative to this kind of a gap right here. You can also see there's this little notch. That little notch should be pretty much in the center between these two edges. If it doesn't look nice and centered and aligned like this, do not try and run. Contact K&I staff and we'll take a look at it and see if it's out of alignment enough to the point where we have to realign it, and then that is something we can do. Prior to running, we also need to check up on the materials we are about to use. On the main screen, I showed you that we could select the pocket we want to move to the active position. Utilize that to move the materials you are going to check into the main position so we can look at them. When checking materials, it's important to understand that there's basically 3 modes in which material will wet and melt, and therefore how to decide when they need filling will depend on which way it wets. All crucibles should be between 50 and 80% full. First, there's non-wetting materials that will ball up in the graphite crucibles we use, materials such as gold, copper, silver, and germanium. Materials like this will generally take a sweep pattern that stays very close to the center of the crucible. These materials will typically wear down somewhat uniformly as the rounded ball of them shrinks. When judging if you need to add more material, the top of the rounded lump is the point you are judging and should reside between 50 and 80% of the way to the top. Second, there's wetting materials, which will wick onto the sides and form a meniscus. Water does this in glass, for example, so it will look a lot like that, except that it'll be solid metal in a crucible. Materials like aluminum, titanium, silicon, nickel, and platinum will behave this way in graphite. It is the bottom of the meniscus that should be judged when assessing the fill level. Lastly, there's non-melting materials, or materials with poor thermal conductivity that only partially melt together, or are sublime instead of melt. Materials such as chromium, aluminum oxide, and silicon dioxide will exhibit this. In the case of aluminum oxide and silicon dioxide, you will find a small group of melted material sitting on top of unmelted material, and with chromium you will find a hole that tends to be bored into the pieces and it remains unmelted, which is pretty much exactly like this diagram. In this case, it is important to watch for deep holes being formed in the material and to refill them as necessary. If a hole is not filled, then the beam will strike the base of the crucible, cracking it and boring a hole into the hearth beneath it, which will damage it. Now that we've checked our materials and loaded our samples, we can close the door and hit pump down. Make sure you're in automatic mode before hitting pump down. Notice that the T section above the roughing valve is green. This indicates that the roughing valve is open and that the chamber is pumping. You can also see this by watching the pressure to see that it is dropping. And you can also see that this is highlighted, which means that you've hit the pump down button. Also, chamber vent is grayed out, meaning that it's running pump down. In addition to that, you can see up here there's a status bar which says pump down, roughing process chamber, and that is exactly what it's doing. Once the pressure goes below 1 e to the minus 1, the roughing valve will automatically close, and then the cryo valve to high vacuum will open. While the chamber is pumping, we can go ahead and set up our recipe. To do this, start off by going to the recipe folder at the bottom taskbar. If it's not there, you can go to Start, and then you'll see Shortcut to Recipe up here. Open the folder and you'll see a list of spreadsheets. Find one that matches the layers you'd like to do, and open it. This spreadsheet is an example of a titanium and gold deposition. Leave the pre-process ingredients section alone. In the IC5 process section, you can see that there's room for up to 10 layers. This process will do titanium as the first layer, and then followed by gold. So let's break this down. Material number identifies the material for the IC5, so that it knows which constants to use for the thickness sensor. You won't have to change this. The rate is the desired deposition rate in angstroms per second. Set this to your desired amount. Between 0.1 and 5 is typically fine. I recommend 1 as the default unless you have a reason for wanting to go faster or slower. Final thickness is the thickness you want for that layer in angstroms. Thickness limit is just a hard stop safety. It should be slightly higher than your total thickness for that layer. The time limit is another hard stop safety in case something goes wrong and you don't notice. Calculate the time you'll need by dividing your thickness by your rate, and make sure that the time limit is slightly longer than that. Do not touch the code deposition section, as that is not a capability our eGun has. For crucible, simply make sure that the crucible is correct. So if titanium is in pocket 2 and gold is in pocket 5, then the crucibles should be 2 and 5 respectively. The last two sections are also unused. When you've set it how you want, simply hit save and close the window. Now that we've set up the recipe, let's load it into the IC5. To do this, we'll go to the Navigator panel at the top, which will bring up this toolbar on the right. Select Recipe from the options. The Recipe panel will then come up. Select the Folder Open button on the bottom left, and it will prompt you to select a file. It will open right up to the Recipes folder. Find your recipe and open it. Once you do this, you will see Sending Data at the top right of the Recipe panel window. Once this stops flashing, your recipe has loaded into the IC5 and is ready to run. Once we reach our desired base pressure and have set up and loaded the recipe into the IC5, we are ready to start the auto deposition process. First turn the key in the eGun power supply to on. Next, hit Auto Start from the main buttons at the top. Then you will see all of these interlocks and starting conditions checked off, indicating that they are met. If you don't see them all checked off, it won't let you run. Notify K&I staff of which ones aren't checked off and we will assist. Then hit Start Process. After you start the deposition, the system will do the following things, which you can observe in real time via indicators on the pumping control panel. They're a bit tedious to point out and not really necessary that you follow them, so I will omit them in this presentation. However, in real training they will be pointed out to you. The following things will occur in order. 1. The system begins rotating the dome. 2. The high voltage comes on. You will see 10,000 volts on the power supply. 3. The sweep controller will begin running a pattern. The green LED grid will animate a representation of that sweep pattern. The LCD screen will stay lit to tell you that a pattern is running. It may not be the correct pattern at this point, but that's okay for now. The hearth will rotate into position to your first layer material. It may rotate to another material first as a default position. This is normal. However, once the hearth is set to rotate to your first layer crucible, the sweep controller will change to the correct pattern. If it does not at this point, you must manually change it. To do this, follow the instructions on the LCD screen. Currently it says press delete to stop. Pressing delete will stop the pattern. Then you will have some options. Option 3 will be run a pattern. Press 3, then hit 000 to clear the current value and type in the desired sweep pattern number. Then hit enter. You will see the new sweep pattern running. It will list it here, and this grid will represent the new pattern. The beam power will then go through rises and soaks, during which the power will be displayed on the IC5 next to power. And lastly, the shutter will then open and the deposition will begin. The crystal will begin measuring thickness. Now that the shutter has opened and deposition is occurring, the main screen looks something like this. The shutter is open, and money symbols will start flowing up in an arc from the bottom of the chamber. Let's take a look at what's happening during the ramp soak part of the process. Physically, the power of the emission from the beam is gradually increasing. This is done to gradually heat the material and allow it to reach thermal equilibriums before continuing to heat up. This reduces spitting, splattering of metals, and greatly reduces the thermal stress in the crucible and hearth due to large thermal gradients. Each ramp phase turns the power up steadily to a certain value, which is then followed by a soak. During that time, the power remains the same, and the temperature of the crucible equilibrates. Once the second soak is complete, the shutter opens. At this point, the IC5 begins measuring the thickness of the depositing film, and from that calculates a rate. The beam power will then be adjusted accordingly to reach the specified rate. Therefore, there is a range that the power will drift within until it stabilizes. After the target thickness is reached, the power ramps down, followed by a cool-down period of 5 minutes before rotating to the next material. During deposition, it's important to monitor the rate and power. You should see power stabilize with the rate, and the two should remain relatively constant throughout the process. If you suddenly see power increasing by more than about 10% and the rate is steadily dropping, that is an indicator that you've run out of material or run to the bottom of the crucible. If material levels are properly checked and maintained, this will not happen during your run. After the cooldown is complete, the auto start button will flash yellow and say continue. Hit that button and the system will automatically close the high vacuum valve and begin venting. When it's done, this large process complete message will come up. Hit OK. You'll then need to go into manual mode and manually vent until the door's seal breaks. Close the vent valve and you can proceed to unload your sample. At this time, you should also check the materials you evaporated once more to make sure they don't need any attention, and to check that nothing strange has happened, such as a crack or hole being bored into them. Simply close the door, go into auto mode, and hit pump down when finished unloading. Wait a few minutes for the crossover from rough vacuum to high vacuum to occur. If it does not automatically occur when the pressure goes below 1 e to the minus 1, then hit pump down again, and it will. Lastly, let's just recap the entire process flow from start to finish. First, we'll load our sample. This involves venting the chamber, checking our materials, loading our wafers, and lastly pumping down. Second, we'll set up our process. Set up the recipe spreadsheet and save it. Load it into the IC5, and then we can begin our deposition. To deposit, turn the power supply on and hit auto start. Correct the sweep if necessary. Then monitor the power and rate during deposition. Lastly, we will unload our wafer. Hit continue when the process finishes, wait for vent and hit OK. When the process completes, then you can finish venting manually. Check your materials, unload your wafers, close the door and pump down once more. Wait for it to cross over to high vacuum, and that's it. Thanks for watching. If you have questions or comments, please email me at alexw@caltech.edu.